Hello, linear algebra. How are you? And happy new year. Whoops, I just did a speako. Hello, multivariable calculus, and happy new year. And in case you're wondering, no, I did not have a voice box implant change. I am getting over a really wretched cold, and I'm guessing you all probably had your fair share of colds this break too, but I hope you all had a great break. Robbie and Eric, it was really fun running into you. And Spencer, thank you for your document with my midterm interims. And for those of you who haven't sent them in, you can still send them to Spencer, who will forward them on to me. Okay, so as promised, this screencast is a listen carefully and take notes only screencast. It is later than I thought I would send this screencast. I think mainly because I wanted everyone to have a long break. Or maybe I should just be honest and say I wanted a long break and didn't even think about this until recently. But then once I started doing this, I kind of got back into the groove. And so it's really fun. Okay, so what I want to do right now is just start with a recall. Okay, this green asterisk I'll come back to in a second. What we left off with right before break was finding the directional derivative of a function at some point x naught, y naught in the direction of some unit vector. And this was the this was the derivation, right? It's the derivative with respect to s. And I may have, what is that? And I may have used d by dt, but regardless, same thing. The idea is the same. That's the most important part. It's the derivative with respect to s of f of x plus su1 comma y naught plus su2, where, okay, and here's what's important, where z is the function of x and y, u is unit vector with components u1, u2, and the line parallel to u passing through the point x naught, y naught is given by x equals x naught plus su1, y equals y naught plus su2. And here's where I may have used t before, but again, that is an insignificant and non-meaningful difference. And again, what you may have recalled, we talked about the fact that when I was doing this derivation in class, at one point I said, what is this describing right here? This expression. When you replace x and y with the parametric equations of that line. And we all agreed that when you sub in x and y from here, x and y, this expression then describes the rate of change of z as a function of s, right? And we talked about the fact that this is describing the rate of change along the quote-unquote path that is above this line, so to speak, okay? Okay, so this is where we left off, and now here's what I want to show you, okay? But now that we have the chain rule, I could find this directional derivative differently, all right? So here's what I want you to look at. We have here, z is a function of x and y, right? And z is a function of x and y means that z is a function of x and y. And here, these equations describe x as a function of s, right? And y is a function of s, okay? And up here, when we took this derivative, everybody, at the end of the day, d by ds of this, right? This is just dz by ds at s equals 0. dz by ds, because this here is s, and I'm finding dz by ds at s equals 0. Well, guess what? If I know that z is a function of x and y, and x is a function of s, and y is a function of s because of these, right? And I'm asked to find dz by ds, if that's what I'm doing, I know using the chain rule that dz by ds equals dz by dx times dx by ds plus dz by dy times dy ds. And look what we have here. We have a brand new way to find the directional derivative. Okay? This is another way of finding what we found above. the directional derivative of f in the direction of u, okay, at some point x comma y. This is describing the exact same thing, exact same thing. Now, once I have dz by ds written this way, here's where we're going to pull some magic. I'm going to do this. I'm going to say, you know what? Let's express this sum over here with vectors. And I'm going to do this. I'm going to say, you know, dz by ds, which is the directional derivative of f in the direction of u, is the same thing as doing this. I can say, let's express that sum as a product, as a dot product of two vectors. And let's call the two vectors, oh my gosh, what is that? Let's call the two vectors vector 1 and vector 2. Okay, would you agree, everyone, that if I were to give you this dot product, that dz by dx, comma, dz by dy, dot dx ds, comma, dy ds, mathematically, this dot product would absolutely equal this, correct? Yes, correct. Well, let's go a little further, okay? dx by ds, what is dx by ds, everyone? Okay, don't forget, this was our x and y. Please pause me and say to yourself or someone next to you or your brother or your cat or your gerbil what dx by ds is and what dy by ds is. Okay, replay me now. Very good. Hopefully you will see that dx by ds is merely u1 and dy by ds is merely u2, or the components of vector u. Okay? And this vector, I could certainly just name it or leave it as dz by dx, comma, dz by dy. I'm just going to use a little bit more of a succinct notation. It's just this, okay? Because dz by dx is just the partial derivative of f with respect to x, similarly for y here. And now, oh my goodness, I'm going to go one step further. If I dot u1, comma, u2, isn't that the same thing, everyone, as just dotting with vector u? Yes, it is. And here is where I'm going to focus on this vector for quite some time. For quite some time, meaning about 5 minutes tonight, okay? This vector is incredibly interesting. It is a vector whose components are the partial derivatives of the function, okay? We have never before seen a vector whose components are the partial derivatives of a function. So special is this vector that we give this vector a new name, okay? We say the gradient of f of x, y, okay? The gradient of a function of x and y, or, okay, del f, all right? This is how you, well, let's do that. Let me do the speaking part next. Okay, hold on. Let's do that. All right, let me just define it. The gradient of a function of x and y is defined as the following: a vector whose components are the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y. Okay? Now, you're wondering, when we write the gradient of f of x, comma, y, there has to be a symbol for this, and there is. The gradient of a function is the same thing as del f. Okay? This symbol here is pronounced del. Del f is a vector. Okay, so the first most important thing to say to you right now is, when you're at a party and someone says, what is the gradient of a function? The first thing you'd say is, well, the gradient of a function is a vector, okay? And you'd say symbolically, this means gradient of f. How do you say this? You don't say upside down triangle f. You say del f, okay? Del f equals this vector. The x component is the partial derivative of z with respect to x. The y component is the partial derivative of f or z with respect to y. Okay, so this is new. I don't want to get into your business here and tell you how to take your notes, but I guess I'm going to anyway. This is new for us. The gradient vector is an incredibly powerful, informative one. So let's go back over here. I'm now going to replace this vector with my new symbol, which is just del f. Okay, and we have this fantastic, succinct, frankly, I think really beautiful because it's so succinct. The directional derivative of f at some point xy in the direction of u is equal to del f dot u. We love this. Don't you love that so much more than this version? The answer is an obvious yes. Okay, let's just work through one example, and then I'm going to have you do some thinking. Not that there hasn't been thinking all the way here. Okay, let's just do an example. Let's say let z, which is a function of x and y, equal 2x squared y minus, I don't know, a natural log of x times y cubed. Okay, and I want to find. Okay, this is just mechanical. The directional derivative of f at the point, let's do e comma 1, okay, where let's say u is equal to 1 over radical 2 comma 1 over radical 2. Okay, so here I've actually given you a unit vector, so we don't have to unitize it. Okay, so let's do it with our newfound idea. So the first thing I want to do here with you is let's just first find the general gradient vector del f. Let's find the general gradient vector del f at any point x comma y. And you'll notice very quickly that it's very much okay to just kind of drop this part of it. Del f at some point x and y, you'll often see in your work or in books or in my work that I'll drop the x comma y and just write del f. Okay, del f is a vector, and the vector is going to have components. The first component is going to be the partial derivative of z with respect to x. That is 4xy minus y cubed over x, right? Derivative of ln x is 1 over x, correct? Comma 2x squared minus 3 ln x, all of that squared, times y squared. Okay, so here's my general gradient vector. And now let's see, where is del f at that point, e comma 1? And I will say what is important, you don't have to have this here, but if you are inputting in particular values for x and y, then you absolutely do need this. Okay, so this is going to equal, let's see, 4e minus 1 over e comma, oh gosh, can you tell that Missy Ann made this up? Minus 3 ln e squared. Oh, yay, that's just 1 and 1. Beautiful. Okay, so here we go. This is the gradient vector. This is del f at the point e comma 1. It is this vector right here. And if you had a calculator, you can go ahead and find those approximate components if you want to, but I'm not going to bother. All right, well now I want the directional derivative of this function f at the point e comma 1, but now in the direction of vector u, and this is just going to equal del f at e comma 1 dotted with the unit vector u, which is 1 over radical 2 comma 1 over radical 2. Okay, and let's not forget here that, all right, hang on a minute. Dot 1 over radical 2 comma 1 over radical 2. Okay, I'm going to ask you go ahead to pull out your calculators and find this dot product because I don't have one handy, but just, plug and chug this, multiply it by 1 over radical 2, and then add it to this plugged and chugged plus that. You're going to get a number, right? A scalar quantity, which again makes sense. This gives you the instantaneous rate of change of z in the direction of vector u. You understand? Let's not forget what the directional derivative means after all. All right, fantastic. So that's just the gradient used in finding directional derivative. But now I am going to ask you some thinking questions. And this is what we're going to pick up together on Monday, a wee 3 days away. So, we have this. We have the directional derivative. Oh gosh, what's happening? Okay, and look here, this is just another notation for the directional derivative of f in the direction of u. So it's just another way of writing directional derivative, right? So this is the derivative of f in the direction of vector u. Okay, so we have this. So I'm going to kind of play with this a little bit. Let's see. Recall something. Recall back in the day. Remember this guy? Vector a dotted with vector b divided by the magnitude of vector a times the magnitude of vector b. What did this equal, everyone? Yes, it equaled the cosine of the angle between the two vectors, correct? Okay. So again, these are two vectors. So what I'm going to do is have you think of something. This is from back in the day. So I could say this, that del f dot u equals, oh my gosh, no, how embarrassing. Okay, so del f dot u really equals the magnitude of del f times cos theta, right? Where did magnitude of u go, you're wondering? Well, magnitude of u is just 1, so I know it's not going to affect this. If anyone's curious as to where this came from, because I think that if you're really rusty, and who knows, maybe you are very rusty after this luxurious winter break, just to be clear, it came from this. Right? Okay, I just multiplied both sides by the denominator. So here's this, right? That's where I am. So here's my question to you. Tell me what value of theta here ensures that the directional derivative value, or the instantaneous rate of change of z in the direction of u, or this scalar quantity, is maximum. In other words, what value of theta absolutely, positively, without argument or debate, would guarantee that this directional derivative is as great as possible? And I'm going to write that question out here. And, this is what we call thinking. It's also a derivation. It's also called something that I've been focusing on, hopefully, all year with you, approaching math conceptually, which is understanding it. Because then you can think of anything, you can handle any question. So my question to you is this: what theta value allows, ensures, guarantees, whatever verb you want, allows this quantity to be maximum? Okay, maximum. And this quantity that we speak of, that quantity is, again, don't forget, the directional derivative of f in the direction of u, right? Or this version, or the general one. Here, okay? That, right? Okay, what value of theta, that's question number 1 to you. What value of theta allows del f dot u to be maximum? Okay, Here's the related question. Second question. Assuming you were able to figure that question number 1 out, what then must be the maximum value of the directional derivative of f at some point x, y in the direction of u? So two questions. What is the relationship between the gradient vector and the vector u? Okay, what angle between them ensures that the rate of change of z is maximum? Okay, what then must be the actual max value of this? In other words, once you figure out question number 1, the second question is saying, what then is that maximum instantaneous rise over run of z? Okay, two questions. Very good. Third question. What then must be the minimum value of the directional derivative of u of f at some point x, y? Okay. And related, what theta value allows, ensures, guarantees, whatever verb you want, for this minimum rate of change to occur? And I guess that's just 4 questions. Why does all of the above make sense geometrically? Okay. All right, everyone. I look forward to seeing you on Monday. Enjoy your last weekend. And I'll see you on the 8th. Happy New Year and good night.